So I wanted to talk about wave-particle duality. I've been reading this book, it's a biography of Einstein. It's really simplistic when it goes into the science, but it still has to go into subtle science. So it's kind of interesting how it manages to do that. But anyway, regardless of that, I've been thinking about this. And, back in at the turn of the century, this was a controversial thing, whether there were um, atoms or not. In one way, this was demonstrated actually by Einstein himself, was by showing the Brownian motion could not be explained any other way. There was no continuous kind of a function where the physics was continuous um, that would explain that. For there to be this Brownian motion, you had to have little tiny particles, because while every little particle um, wasn't enough to move. They could see little tiny bits of pollen and stuff in a water solution wiggling under a microscope, just randomly, the Brownian motion. And that could not be explained by classical mechanics, because it should really swirl around. It should do a little swirly thing. But it just jostles. But is explained by particle collisions in combination with statistics, and that's what Einstein had shown. Okay. Now, the thing about particle wave duality is you have to think of it like this. Okay, with the wave, let's say you throw a pebble into the water. Just a pebble. Tink. It makes a little ripple, a very clean ripple, because it's a little short-lived splash, and the ripple goes out. That's a wave function. That's a wave form. The front of that is called the wave front. It's a circle. It can be deformed into other shapes, but it ripples out in a circle. A particle is more like a bullet. It's a very different thing. So they were wondering if photons were particles, like a bullet that would shoot out from a cannon, or whether it was like a ripple, because the ripple is the circular shape expanding, right? Particle's very different. It's a bullet. Now, how can you tell if it's one or the other? Well, you can do various things with it when you have millions of them that show that wave behavior. Maxwell's equations, that was pretty much shown. But let's say we lower down the size of the ripples. So now when you are creating a radio wave, what you have is a wire antenna stuck, let's say, up in the air, and there's a bunch of electrons in it. By putting a magnet on and off, what you can do with this switch, an electrical switch, you could cause those electrons to jostle. And as they do, a ripple comes out. It's just like the waveform. A ripple of radio waves in all directions comes out. But if you make a tinier and tinier pebble, you get a littler and littler ripple. And you can do it to the point where it's so small, just one little thing comes out called a photon. And it's like a bullet, it's like a particle. It comes out in a random direction from the antenna and shoots off. You've just gone cha-ching, like one time, and one of these shoots off. Okay, so it's like a particle, because you could put up a screen, a photographic screen that would catch radio waves, and it would catch this, and you could see it's like a particle. Dink, it shoots in a screen like a particle. But there was questions as to why it behaved like a wave then. Now, Planck and people like this originally simply thought, well, it's a feature of the emission. Okay, that it acts in these quanta and particulate ways. So the light isn't really that way. It's got to be a wave. I actually still believe this. But to look into this, what can you do? You have a photon that shoots off and strikes a photographic plate and makes a single dot like a particle, like a bullet. Well, what you could do is you could put those two slits in front of it. Now, this is a discriminating thing between a wave and a particle phenomenon. If you shoot a bullet at a screen, it'll either hit the mask, or it'll go through one of the two slits and make the mark on the screen, on the wall behind it. Right. So if you jostle the electricity just low enough so that one photon comes off, zing, it goes, and it does that. Oh, question answered. It's a particle. Because if a wave hits a screen, what happens is most of the wave is cut off, right? And where the wave is allowed through, little ripples will come through, and both of those little slits will kind of act a little bit like a cone-shaped point source. It'll be ripples, they'll be arcs of circles instead of circles, and they're not actually quite arcs of circles, but they start to approach being an arc of a circle. The further away you are, the more it would be like that was a point source, that little slit. And then the wave front hits that, and because it's a wave front, it goes through both slits, it would hit the screen. But the thing is, it doesn't make just one mark. If you have a screen that could record it, like the electromagnetic fluctuation or something, it would record all over. Okay. And so the problem is that though when you fire it through as a bullet, if you are patient and take your time, you'll see as the bullet dots fill in, they make that wave pattern that you would expect to get if it was a wave. So somehow together, over time, one at a time, they're acting as a wave. Well, there's no way for the past photons to be interacting with the future photons, not by any theory of time that we've come up with. So it seems like the single photon really is still a wave. And the puzzle is why it appears like a bullet, or why a bunch of bullets can act together as a wave. But see, the classical concept of a particle doesn't explain how it would act like a wave. It explains how waves would travel through it, but not how it would act like a wave. Okay. So it has to be the other way around, that the particle really is always a wave, and somehow the wave nature is what we need to understand. And we've reached an edge of human understanding, trying to understand that. So the thing is, back to the antenna, when you put just enough energy to send one photon off that antenna, okay, the point is, at that point, that thing is a particle. But what's weird is it's a wave. It doesn't mean it's a little ripply particle that's wiggly. No, it means it's a ripple. It doesn't really go off in that one direction. We don't know why we see it in that direction instead of another one, because with the two-slit experiment, we can see it actually is going in all directions, and that's how it has its wave nature. String theory, other higher dimensional theories are ways of trying to explain this by just saying, hey, all of those possibilities are real. For some reason, we're seeing a subdimensional cross-section of it, which is the speck on the photographic paper that we see. But really, there's the whole diffraction pattern there, and there's all these other dimensions that exist physically, where if you could see them all at once, you'd see the wave pattern just with one photon. Okay. All right, cheers.